In example number 2, we're going to be using proof by mathematical induction to prove that this expression 9 to the n plus 3 will always give me an answer with no remainder if divided by 4. We start, as we did before, by proving that the statement is true for n is equal to 1. If n is equal to 1 in this statement, then I'm going to have 9 to the 1 plus 3. Well, that gives me an answer of 12. And I definitely know that 12 is divisible by 4. In other words, I have proven my statement true for n is equal to 1. Now we must move on to number 2, which is our induction. The first part of our induction must be to assume that the statement is definitely going to be true for n is equal to k. So the first thing that I'm going to do is I'm just going to take my statement and I'm going to replace the n with a k. But that isn't where I end when I try and prove divisibility, because the assumption says that the whole statement is true. In other words, it's stating for a fact that if I divide that expression by the number 4, I am guaranteed to get a number which has no remainder. In the second part of induction, I need to prove that the statement is definitely going to be true when n is equal to k plus 1. If I'm going to be proving this, then I need to prove that 9 to the k plus 1 plus 3 is going to be divisible by 4. Now, I can't write divisible by 4 over here because that is what I'm proving. If I want to do this, I need to somehow try and get the information that I used in my assumption and put it into my proof, the second part of induction. So let's go back to the assumption. In my assumption, I now want to try and get 9 to the k on its own. In other words, if I times the right-hand side by 4, I'm going to get 9 to the k plus 3 is going to be 4 times r. And then taking the 3 across, I get 9 to the k is going to be 4r and minus 3. This is a nice, useful piece of information, and it looks like I can use this in the second part of my induction when I am proving for n is equal to k plus 1. Now what I need to do is I need to take the statement that I've got and try and break it up so that I can get 9 to the k on its own. As soon as I've got that, I can replace that by 4r minus 3. The first thing that I'm going to do is I am going to break up that factor 9, because the factor 9 was described by k, and the factor 9 was described by 1. Can you see that now I can actually take the information that I've got over here from my assumption, and I can put that in the place of 9k. So in my next step, I'm going to say that that is actually the same as 9, which is now my coefficient, all times by 4r minus 3, and then still plus 3. By distributing the 9 into its bracket, I'm going to get 36r minus 27 plus 3, and that is going to be 36r minus 24. If I take out a common factor of 4, I have 9r minus 6 in my bracket. Well, if I've got a number like the number 9r minus 6, and it's times by 4, it means that that whole number must be divisible by 4. In other words, I have proven that the statement is true for n is equal to k plus 1. So concluding our proof part of induction, we must state that the statement is true for n is equal to k plus 1, n an element of the natural numbers. And finally, as we proved that that statement would work if n was 1, and we also proved that that statement would be divisible by 4 when n was equal to k plus 1, it stands to reason that the statement must be true for n is equal to k when n is an element of the natural numbers. we have now proven through mathematical induction that 9 to the n plus 3 is always going to be divisible by 4.